we present CylinderDepth, Cylindrical Spatial Attention for multi-view consistent, self-supervised surround depth estimation. A novel geometry-guided method for multi-camera rigs that predicts dense metric depth. Surround view camera setups allow for dense and low-cost 3D perception with a 360 degrees field of view. Due to the minimal spatial overlap between the images, depth is for the most part estimated for each image in a monocular manner. However, using a single shared depth model across all views can lead to inconsistencies in the predicted depths. This means that the same 3D point, when observed in multiple images, may be predicted to be at different 3D locations for each image. The inconsistencies in monocular depth estimation of multi-view images arise from the limited and local receptive field of each image, particularly knee border regions. Cross-view attention can help address this limitation by sharing the encoder features across views and extending the receptive field beyond a single image. However, in fully learned unconstrained cross-view attention, each token attends to all tokens across all views, even though most correspond to less relevancy in content. As a result, feature sharing can become noisy and unreliable. We address these issues by exploiting the geometric relationships between the images to constrain attention to geometrically plausible regions. Note that the upcoming steps are applied to the feature maps, not to the RGB images. The RGB images are shown only for better visualization and understanding. We project the pixel positions into a shared cylindrical representation using the initially predicted depth together with the given camera intrinsics and relative orientation parameters. This establishes neighborhood relationships among tokens from all images, such that overlapping regions are mapped to nearby locations on the cylinder. Based on the geodesic distance between positions of the tokens on the cylinder, we use a truncated Gaussian kernel to define and weight cross-view attention. This way, we constrain attention of a query token to only geometrically plausible regions. Our method achieves state-of-the-art results on DDAD and nuScenes in both multi-view consistency and overall depth accuracy, as shown by quantitative and qualitative evaluations.